Okay, so when we ended off yesterday, we were looking here at question number 2. Okay, we were trying to calculate the tension in the rope that was connecting these two boxes. Okay, now what we had to remember was everything we calculated the first time we did this question still applied to this second time we saw the question. Those things would be that we had already calculated the acceleration to be 0.36 meters per second squared in a forward direction. Okay, we had also calculated, we also knew the total amount of friction on the whole system. That still applied as well, as did this applied force here. Okay, so those things were all still true. And then I told you there's actually 2 ways to solve this question. I can solve it using the 10 kilogram box, or I can solve it using the 20 kilogram box. Either way will work. There's one extra step to solving it using the 20 kilogram box. It's a simple step, but it's just one extra one. Okay, so let's just kind of quickly go over what we did with the 10 kilogram box. Okay, I know the mass of the 10 kilogram box, and I know the acceleration of the 10 kilogram box. What can I calculate right now about the 10 kilogram box? Which force? I have mass and acceleration, that calculates net force. Is that an important thing for me to know? Really important. Okay, so I'm going to do that first. Okay, F net equals m times a. And we've said on basically every question we do, you're going to use both methods to calculate net force. M times a and the vector sum of all forces. And the same is true here. Okay, so m times a, 10 times 0.36. All right, so my net force is 3.6 newtons forwards. I'll just make it positive for now. All right, everybody with me so far? All right, now I'm going to go over here and I'm going to draw my free body diagram for just the 10 kilogram box. There's 55 newtons worth of force acting forwards on the 10 kilogram box. That's the force of the hand pulling that rope. Backwards, there's a force of friction, and this question told us that the friction on the 10 kilogram box is 14.7 newtons. Since friction always resists, that's backwards, 14.7 newtons. And the question wants me to calculate the force in the rope that's connecting the two boxes. So that rope connects the 10 kilogram box to the 20 kilogram box. If I'm the 10 kilogram box, what does that rope feel like it's doing to me? Pulling me backwards. There's my third force. Okay? The third force acting on the 10 kilogram box is the one that we're supposed to calculate. Okay? It's the tensional force in the rope connecting the two boxes. Right? It would be kind of like if I was just walking along, okay, normally, and then I do the same walk, but I grab like a wagon, okay, and I pull it behind me. Right? When I'm pulling that wagon, does it feel like the wagon is pulling me back? It does. Okay? That's the force we're trying to find. That force that's now present because I'm dragging something behind me. Right? Okay, so I know 3 out of the 4 forces. And since I know that net force is the vector sum of all forces, so that would be the applied force. Okay? That's that force there. Okay? The force of friction, the 14.7, and the tensional force. Okay, I know if I add all those up, they add up to the net force. Everyone okay with that? That's my vector sum of all forces step. I already know what F net is. It's 3.6 newtons. I calculated it here. So I know this, and I know this. Can I calculate the one I don't have? Okay, so like I said, in every question you do, you're going to do both methods of net force. Vector sum of all forces and m times a. So I'm going to manipulate this for Ft, or the tensional force. That's going to be F net minus the force of friction minus the applied force. Now, direction matters here. Okay? Forwards is going to be positive. My net force is forwards, so that's positive 3.6 minus negative 14.7. Okay? Because that's friction. Friction's acting backwards. Okay? Minus 55. That's the positive forward force. Okay, so when I do this, Okay, I'm going to get 3.6 minus negative 14.7 minus 55. All right, so I get negative 37 newtons. Okay, everybody all right with that? Okay, that's the answer they got, except they didn't put negative on it, right? The reason they didn't put negative on it is because in the truest sense, a tensional force, that's a force that's in a rope, actually acts in both directions. Okay? The reason I put the negative on it is because from the perspective of the 10 kilogram box, that force is backwards. Okay? But if I'm just looking at tension, there's 37 newtons worth of tension in that string. It actually pulls equally both directions. All right, so that's solving it using the 10 kilogram box. Okay? It's slightly different to calculate it using the back box. Okay? It's similar steps. There's just one step I have to add. Okay, so let's draw the free body diagram for the 20 kilogram box. There are only two forces acting on the 20 kilogram box. What are they? What's pulling it backwards? Friction. Okay. Do I know how big that is? I don't, but I can calculate it because I was told the total friction in the system is 44.1, and 14.7 of that is on the first box. So whatever's left is what's on the second box. That's the extra step, okay, that's involved in using the back box. It's just having to calculate how much of that friction is on the back box. Okay, so we take our 44.1 and subtract the 14.7. All right, so there's 29.4 newtons worth of friction on the 20 kilogram box. What's the other force acting on that box? What's pulling that box forward? The what?
55.
Actually, the 55 is only acting on the 10 kilogram box, right? The 20 is not attached to the hand directly. But the force that is here is the one they want me to find. Right? From the 10 kilogram box's perspective, that was a backwards force. But that force is pulling forwards on the 20 kilogram box. Okay? Those are the only two forces acting on that box. Okay? So, can I calculate the net force acting on the 20 kilogram box right now? I know it's mass and I know it's acceleration, right? This is that all parts of the system accelerate at the same rate idea. I have to remember that in order for this to work. All right, so 0.36 times 20 kilograms is going to give me 7.2 newtons forwards. So the net force on the 20 kilogram box is 7.2 newtons forwards. That net force is the result of the force of friction and the tensional force they want me to find. Do I know 2 out of the 3? Yeah. So I can find that tensional force. Okay? The tensional force will be F net minus the force of friction. So that'll be positive 7.2 minus negative 29.4. Is that going to give me 37 again? Pretty sure it will. But this time it's positive, because from the 20 kilogram box's perspective, that force is pulling it forwards. Okay. You're probably looking at that and going, wow. Okay. How much math was in that question? Not a lot. I had to multiply a couple of numbers, and I had to subtract a couple of numbers. That's it. That's what you're going to find in this unit, guys. There's not a lot of challenging arithmetic in this unit. What's challenging here is understanding. You have a conceptual difficulty with these kind of questions as opposed to a mathematical difficulty. This is where physics ceases to be about math. Okay? Like in unit 1, yeah, okay. There's going to be some trig still in this unit from time to time because net force is the vector sum of all forces, so occasionally we're still going to have some vector stuff to do. Okay? But when it comes right down to it, most of the difficulty in these questions is conceptual. That is, looking at it and being able to see what's happening. Visualize, okay, there's a force here, there's a force here. How is this force affecting this thing? Okay, that kind of stuff, and understanding that. That's where the difficulty and the challenge lies in Unit 2, not in your ability to do the math. Okay.
So when you're doing like the 20 kilogram box, you don't have to include the number of like that's the force that looked at him.
No, because that force is not directly acting on the 20 kilogram box,
Okay.
right?
So it's just the same like FA plus like force of friction plus force of tension, except you don't include that.
Right.
Okay.
I mean, the tensional is kind of the applied force on that box,
Okay.
yeah?
Mm-hmm.
And our force of friction was different. The bigger box has more friction. The heavier an object is, if they're on similar surfaces, the more friction there will be. Right? Think about it. I got an empty cardboard box, right? Like let's say I got a fridge delivered. Okay, it comes in a really big box. That box is empty. I can push that box along the floor, no problem. There's barely any friction, right? But if that box has a fridge in it, there's way more friction because the fridge pushes against the floor a lot more than the empty box does. It creates more drag. Okay, so the heavier something is, the more drag it's going to produce. All right. Here's the next kind of system question. Okay, this is where things really get conceptual. Okay, so I've got this situation here: vertical pulley and two masses hanging from it. Okay, now I'm holding them obviously because if I didn't, what would happen? In this situation where the right-hand side is a 35 kilogram mass and the left-hand side is a 25 kilogram mass, if I let this thing go, what's going to happen? Right, the 35 kilogram mass is going to drop and the 25 kilogram mass is going to go up. Okay, I mean, you guys are looking at me like, it's obvious. But that's an important thing to realize. I have to be able to look at this situation and go, what would happen here? Okay, that's an important thing, part of our understanding, okay, in order to do these questions. All right, now we got to look at it even deeper. I know what's going to happen. Why? What forces are acting in this system right now, assuming that that pulley is frictionless?
Gravity is acting on both of the masses, and since one of the masses is bigger than the other, it accelerates down.
I don't think I could have said it better myself. Okay, gravity is acting on both masses, but because one of the masses is bigger, there's an imbalance. And as a result, one of the masses will accelerate down and the other will accelerate up. Okay? Even though they're accelerating in different directions, will they accelerate at the same rate? Yes, they have to. It's a system. If they don't accelerate at the same rate, either one catches the other or the rope breaks. Okay? That's not going to happen.
Isn't one of the accelerations going to be positive and one of the accelerations going to be negative?
They can have different directions, but they have to have the same magnitude
Yes.
because they're connected. But yes, one will be positive, one will be up, one will be down. Okay, so the force, or the two forces that are acting in this system are the force of gravity and the force of gravity. Okay? I know it's the same force, but it's in two different places. Okay? Can I calculate those two forces? Yeah, because force of gravity is just m times g, right? Okay, so the force of gravity on the first one, on the 35, all right, so we're looking at 343.35 newtons. Okay, and then this one here, 245.25. All right. I want to calculate. It says, well, determine the motion of each object once the objects are released. I would probably word this question, find the acceleration of the 25 kilogram mass. That's how I would word this question. What's my next step? I know these things are going to accelerate at the same rate, right? And that's because they're part of the same system. What can I do with their masses right now? Combine them, exactly. Okay? Anytime I have a pulley, I essentially have a system with one mass. That mass is distributed in two places, but once I know the forces acting on the individual parts, I want to combine the mass and talk about those forces acting on the system as a whole. So I simplify this to this. This is really what's going on. 60 kilograms worth of mass is being pulled in opposite directions by these two forces. Is everybody okay with that? Okay. It's a lot simpler to look at now that it's one mass in one place. Okay. And effectively, that's what's going on here. The forces that are acting in this system have to accelerate 60 kilograms worth of mass. And we know that the two parts are going to have the same magnitude. This is how we get it. Okay. So now I can say that F net is the vector sum of all forces. So I'm going to have my 343.35 minus 245.25. That's going to give me 98.1 newtons. So the net force in this system is 98.1 newtons down. I mean, it'd be down no matter what, but it's down this way on this side. Okay, in the favor of the 35 kilogram mass. Okay, now that I know this number, can I find the acceleration? Yes. Okay, and this is where people would mess up. If I worded that question, find the acceleration of the 25 kilogram mass, what would people do here? Use 25. They forget this is a system, all of it is accelerating, all 60 kilograms. Okay, so when we do that, okay, we're going to have our 98.1 divided by 60. All right, so the acceleration of the system is 1.6 meters per second squared. Since I worded the question, I want the acceleration of the 25 kilogram mass. My answer is now 1.6 meters per second squared, up. That's how it can be different, okay? It's that slight little detail, but I have to say, because it's the 25 kilogram mass, that it's up. Acceleration to vector quantity. For them, the way they worded this, I can't put a direction on this. I can only give the magnitude because the two parts of the system move in opposite directions. So I can only say that the system moves at 1.6 meters per second squared. Everybody all right with that? All right, so those vertical pulleys, okay, in fact, all pulleys, whether they're vertical or whether they're at a 90-degree angle, doesn't really matter, even angled like this, okay, they all work the same. And that is that you have to find all the forces acting, combine the mass, and draw it simply. Draw it like this. There's this force pulling to this side of the pulley, and this force pulling to this side of the pulley. Then find the acceleration. Find the net force, then find the acceleration. Okay? But with all systems, you got to combine the masses when you're talking about the whole system. Okay, try this one. It works very much like what we just did. Okay, so you have, okay, the table being a horizontal frictionless surface. Okay, so you don't have to worry about any frictional forces. The pulleys are frictionless. The rope is, well, they always say a light rope, which means the rope has no mass on it. Otherwise, you'd have to include the mass of the rope as part of the system. But okay, we're going to say it's a light rope, imaginary. Okay, pail B has a mass of 8 kilograms. Okay, pail C has a mass of 6 kilograms. And the tire is 20. Okay, I want you to calculate the acceleration of the system. That's what they're asking for, the acceleration of the system here. Okay, so what are the forces that are acting in this system? Gravity, yeah, in two different places. All right, so we're going to have force of gravity here on the first pail. Okay, so that'll be 8 times 9.81. Okay, so 78.48. newtons, and we're going to have the force of gravity here. Okay, 6 times 9.81, so 58.86 newtons. Okay, so those are the only forces that are in my system. So now I want to simplify this diagram by essentially taking the pulleys out of it. Okay? I just want to look at how much mass there is in the system. All right, so that's going to be 34 kilograms. Okay, it's being pulled this way. Shorten that arrow. And this way by 58.86 newtons, and this way by 78.48 newtons. All right, what can I calculate right now? Bless you. I can calculate net force, and I should do that. Okay, it's one of the most important things I can have in a Newton's second law question. So we'll have 58.86, okay, plus negative 78.48. I'm just saying that because it's to the left, and left is usually negative. All right, so we're going to have negative 19.62 newtons. Everybody all right with that?
Are the pails pulling the tire?
Yes.
Okay.
The whole thing is going to go, right? They're all connected.
All right.
Okay, like the rope is tied to the pail, tied to the tire, tied to the tire, tied to the other pail. Yeah? Okay, so now I know my net force. Now that I know my net force and the entire mass of the system, what can I calculate? Acceleration, right? Okay, so F net equals m times a, so a equals F net divided by m. That's going to be our 19.62, okay, divided by 34 kilograms. Okay, so the entire system will move at 0.58 meters per second squared. Okay, I cannot put a vector on that because the 8 kilogram pail is going to fall. The tire is going to move to the left, and the 6 kilogram pail is going to move up. All right, I can't give a vector because all three parts of the system move in different directions, but they all move at 0.58 meters per second squared. Okay. Everybody all right with that idea? Okay. So now they want you to do this calculation using that same diagram, okay, except now they're changing the masses. Okay, so I'll just bring the picture over and change the masses on there. Okay, so now you have that picture. Okay, so now you can do this. So the mass of pail B, that's this side, is increasing to 12, and you're not changing the mass of pail C. Okay, and now they want the acceleration of the tire. Not the system, the tire. All right, give that one a try, and if you get that one done, then try looking at number 2, where they replace the car tire, or replace it with a tire that's only 15 kilograms instead of 20. Okay? That goes back to the original settings for the pails. We're looking for the acceleration of the tire in question number 1. Okay, and pail B has been increased to 12 kilograms. Right, so this is now 12. This stayed at 6. Right, so this force of gravity here is still 58.86 newtons, but now this one is bigger. Okay, so we're going to have our 12 times 9.81. Okay, so not divided, 12 times 9.81. Okay, so 117.72 newtons. All right, so now basically everything else, okay, works similar to how we did the last question. Okay, we're going to have 18 plus 20. Okay, is 38 kilograms for our total mass instead of 34, right? And we're going to have 58.86 newtons going that way, and 117.72 newtons going this way. Okay, and we calculate our F net. Okay, so 117.72 minus 58.86 should give us 58.86, right? Pretty sure. Yeah? All right, so our net force is 58.86. Divide that by the mass, 38 kilograms. And our acceleration of the tire will be 1.5 meters per second squared left. They asked for a specific part of the system this time. Tire is going to accelerate in the direction of pail B, that's to the left. Okay, so we should put a direction on that, right? And number two, same idea, calculate the acceleration of each object. So we would do the same calculations, just changing some of the masses, okay? And for pail B, we would have the acceleration would be down. For pail C, it would be up, and for the tire, it would still be to the left. Just different numbers, same calculations. Okay. All right. I want you guys, instead of going on to these static questions, we'll talk about those after Thanksgiving. Okay. I want you guys to work on a few of the ones from the worksheet, the Newton's second law worksheet. I will bring that up here. And I'll have you work on a few questions from there so we don't go into too much new stuff. So you had kind of basic Newton's second law stuff on Wednesday. You got kind of basic / systems yesterday, a little bit more system stuff today. And then next week we'll talk about static questions. Static Newton's second law questions are one in which the net force is 0. Right? So there's no acceleration, but you are being asked to find individual forces within the system. If there's no acceleration, what's the net force? 0. Yeah. So we'll be dealing with Newton's second law questions where there's no net force, and we're being asked to find some of the individual forces. Right. So I would like you guys working on questions like 1 through 12, let's say. Okay. Don't need to go beyond that. Right. And that's on page 2 of your workbook. And they're really straightforward. Like the first one's just n times a. Super easy. Florence, question?
Do the devices not show that?
Nope. Go ahead. Yep.